In this module, we will give you a brief overview of recent scientific discoveries related to thunderstorm development, how they apply to the multiscan radar, and how this affects the interpretation of the weather seen on the display. Thunderstorms can be described in two ways: what you can see with your eyes, what is visible, and what the radar can see, what is reflective. The tops of thunderstorms are composed primarily of ice crystals and are poor reflectors of radar energy. Thus, thunderstorms have both a radar top and a visual top. In most cases, the extent of the thunderstorm threat extends well above what the radar can actually see and includes both the cell top and the thunderstorm-related turbulence that is above a growing cell. As a result, the actual threat must be inferred based on an assessment of the cell. You already do this in manual mode utilizing various radar techniques. In a moment, we'll describe how Multiscan accomplishes a similar task in auto mode. But first, let's look at how weather varies based on geography. The green, yellow, and red colors on the chart equate to the standard radar reflectivity levels. The right-hand curve shows the typical reflectivity of mid-latitude land-based cells. The left-hand curve equates to the typical reflectivity of equatorial oceanic weather. Above the freezing level, the reflectivity of oceanic cells falls off very quickly. What this means is that at cruise altitudes, a land-based thunderstorm that is right on the border between yellow and red will not even show up on the display over the ocean. Note these weather pictures and how closely they correlate with the chart. The right-hand cell has significant convectivity that provides excellent reflectivity characteristics and gives the cell considerable mass. In contrast, the oceanic cell on the left has much less mass and much lower reflectivity. In recent years, scientists have used new weather satellite systems to analyze and catalog these weather characteristics, with the result that today robust geographic weather models are available. Rockwell Collins engineers have incorporated these weather models into a worldwide database that resides inside the radar. Using a 10-degree by 10-degree geographic grid, weather cells that are detected by the radar are analyzed based on geographic position and time of year, and the inferred threat is displayed for the flight crew. Let's look at some real-life examples. Our first test case takes place over the island of Celebes in Indonesia. This is an equatorial land-based cell and is moderately difficult to display properly. Note the small cell forming under the overhang. The radar display shows a shear action within the cell that ends with a proper display of the small cell. Cells are also visible at 70 nautical miles, and two cells are coming on the display at 160 nautical miles. The next example occurs over the Bay of Bengal. This is a typical lazy equatorial oceanic cell. The majority of the convective activity is low in the cell, and the blow-off meanders up to the aircraft altitude. The radar is doing an excellent job of painting the cell core. However, the blow-off is non-reflective and is not seen on the radar display. This type of cell poses little threat to an aircraft at cruise altitude, and a green display is a proper threat indication. Now let's move across the Malay Peninsula to the Gulf of Thailand. The radar is doing an excellent job of displaying a very low reflectivity ridge line at 50 nautical miles. Note that in order to provide an accurate representation of the majority of low reflectivity weather cells, the radar is very sensitive in these environments. On occasion, this sensitivity will result in over-representation of cells, or the temporary display of weather that is below the aircraft flight path, such as these small cells at 20 nautical miles. Our next look at the weather occurs over Madagascar. Again, this is an equatorial land-based cell, and thus it is moderately difficult to accurately determine the cell height. Note that the cell is slightly below the aircraft altitude, and as the aircraft approaches it, the display presentation diminishes. However, the cell is clearly convective and turbulence will be present above it. Therefore, the radar is doing a good job of displaying the inferred threat. Finally, we'll move to the country of Georgia. This cell is a mid-latitude land-based cell and is therefore relatively easy to display. Note that the intervening cell below the aircraft is not displayed. A quick note, there have been some reports of weather being underrepresented below flight level 200. This appears to occur predominantly in upper latitude or mountainous regions. If you operate in these types of regions, please refer to the Rockwell-Collins Service Information Letter that is included in this CBT. In summary, every cell has a radar top and a visual top, and the non-reflective inferred threat is displayed based on the cell's characteristics. However, these weather characteristics vary significantly based on your geographic position and the time of year. Multiscan's use of an internal weather database enables the display of non-reflective weather, but the increased radar sensitivity that enables this will occasionally result in overrepresentation of cells or the temporary display of cells that are below the aircraft flight path.